start this lesson. Okay, so welcome to class, guys. Today we're finishing up Chapter 5, Section 5.7. And you'll notice that the title here should be sort of familiar. We've already talked a lot about inverse functions, and we've also talked about radical functions, for example, finding their domains. And what we want to do is sort of tie the two of these together in the context of polynomials, okay? So a lot of what we're going to do today is just going to be review and just reminding you of this process of finding inverses. But what we'll focus on today, because of the radical function business, is how to restrict domains, okay? But I should say that even though we'll sort of focus on it in class today, in Infinity, I think there's maybe one or two questions along these lines where you have to actually restrict the domain. But it's important that we understand why we're restricting the domain and when we can find an inverse. So we'll be focused on finding inverses of invertible polynomials. Now, invertible here just means that an inverse actually exists. And if you think back to when we were covering functions, the idea of an inverse existing was the notion of the horizontal line test, right? And we said that functions that pass the horizontal line test are called one-to-one functions. So if we have a polynomial function that is one-to-one, then we should be able to find its inverse. And this already rules out a bunch of polynomial functions. So any polynomial function where the leading coefficient has an even power, right? So a polynomial of even degree will have the property that in the long run, right, the end behavior, both ends will go to positive infinity or both ends will go down to negative infinity, a lot like a parabola. And because of that, those functions will never be one-to-one. So they will always fail the horizontal line test, and there will not be an inverse. And so this is why, for those types of functions, we'll have to think about what's called restricting the domain. And once we restrict the domain, we'll be able to find an inverse for those guys, right, in our so-called restricted domain. And this also happens in other places in mathematics as well. So if you take a course where you're going to cover some trigonometry, then there, a lot of the functions do not have the property of being one-to-one. And you, again, will have to restrict your domains, right? So this idea of restricting a domain is important. It's not going to come up so much in Infinity. What will come up in Infinity is sort of practicing your algebra with finding inverses. And I guess for a lot of you guys, you know, just looking over the midterm, that was a question that people sort of struggled with. So I think people had the sort of the process down, but maybe some of the algebra got a little bit difficult. So we'll go through and practice some of those things right now. And then I'll try to, because there's not a whole lot of new topics, go into Desmos and sort of look at the graphs and remind us of what things mean sort of geometrically in the plane. Okay, so again, just coming back to a reminder of what we mean by an inverse. This is going to play a really important role in the next chapter when we talk about logarithms and exponential functions, because those will end up being inverses of one another. And if you have two functions, just as a reminder here, let's say f and g, then we say that f and g are inverses of one another if the following is true. When I plug f of x into g of x and compute g composed with f, I get an output of x. Or vice versa, you could plug g into f of x and you get an output of x. And remember, I think I mentioned to you guys last time that you only have to check one side of this composition here and you get the other one essentially for free. But this is the definition of what an inverse is. And in some sense, you can sort of think about g and f as undoing each other, right? So like if you were to you know, have 3 times x, you would divide by 3. And so here you're thinking about the g and the f as sort of taking that input x and undoing one another and giving you back x. And we'll sort of think of inverses precisely in that way when we talk about logarithms and exponentials. We'll just sort of like define a logarithm to be the function that has this property. Okay, so this is a really good section to set us up for the next sort of chapter, but also to tie together some of the ideas we've been looking at on polynomials. Okay, so there was a question like this on the midterm as well, right? So there, we weren't asking you to check if it was an inverse, but we were asking you to compute g of f of x and f of g of x, right? In some cases, you should have gotten down to just x on some exams. In other exams, it didn't simplify nearly as much, but That's sort of the process we're looking at. So let's just look at an example and remind ourselves of this, right? So here we have two functions. One is f of x plus 5 divided by 3. And the other is what we're going to denote by the inverse. And remember, f with the -1 up there in the exponent just means the inverse of the function and not 1 over f of x. There were a couple of students that made that mistake as well on the previous midterm. But again, it just means the inverse function. And in this case, the inverse function is going to be 3 times x minus 5. We're going to review here in a moment how you go back and forth. If somebody gives you f of x, you should be able to find f inverse. And if somebody gives you f inverse, you should be able to find f. But before we do that, we just want to check the definition, okay? And again, the definition is this thing that we're talking about here. F and G are inverses if when we compose them together, we get F. So here we're going to look at composing F with F inverse. And we're going to look at F inverse composed with F of X. And because these two functions undo one another, when we evaluate these, we should expect to just get back X, okay? So you can think about this function f as sort of undoing what f inverse does and vice versa. Okay, so let's just go ahead and remind ourselves of function composition and how this works. So for this one, you're going to plug in f inverse into the function f, right? So you can write it like this. This is going to be equal to f of, and we'll just replace f inverse with its formula, right? So what's the formula in this case? It's 3x minus 5. Okay, so that's just from this formula here on f inverse, okay? And then what you'll do is you'll evaluate this function f at 3x minus 5. So everywhere that you see an x here on this equation, you'll replace it with 3x minus 5. So here what you'll get is, I'm going to put it in parentheses, 3x minus 5 for this x here that I have sort of circled. And then there's a plus 5, and then the whole thing is divided by 3. And just to highlight, let me put it in yellow here. This 3x minus 5 was the input from the function, right? So that's what I'm replacing that x with in the formula for f of x. And you'll notice here that now you have -5 plus 5, so those two cancel each other out. And that gives you 3x divided by 3. The 3's then cancel out, and you're left with just x. Okay, so we checked that f composed with f inverse gives us back x, right? And remember, when we're sort of thinking about the function as being sort of this machine that has an input and output, this is just sort of saying that, yeah, f inverse is really f running in reverse, right? So going from the output back to the input. Okay, and that's where we got this formula from, right? We actually looked at that picture and looked at it in reverse. Okay, so that's f of f inverse, but now let's also do f inverse of f, right? Because it's going to be slightly different than what you're seeing here. And I'm going to move over here just so we have a little more room. And now we're going to compute f inverse of f of x, okay? Now what we do is we take the formula for f of x and we plug it into f inverse. So that means something like this, f inverse of x plus 5 over 3. So again, all I'm doing is replacing the f of x here with the formula that was given. Now what you want to do is focus on the formula for f inverse, and that's here. And what it does is it takes its input x, it multiplies it by 3, right? And then it subtracts 5 from it. So everywhere I see an x here, I'm going to replace it with this x plus 5 over 3. So here, we'll get x plus 5 over 3 times 3, and then minus the 5, okay? And again, I'm just going to highlight here in yellow where this x plus 5 is going. It's going right here into that formula. And you can see this is just that same formula that we're seeing for f inverse, just everywhere there's an x, we're replacing it with x plus 5 over 3. And then we go through and simplify. This time, instead of the 5's canceling first, the 3's cancel first. And we're left with x plus 5 minus 5. And then plus 5 minus 5, that's just 0, so we get back x. Okay, so that's just a reminder here of how we check two functions are inverses of each other, we compose them, and we expect to get back x. In order to do this, you have to do some simplification, though, okay? Again, that's just back in the definition. Now, one of the implications of this is that if you know the domain of f, that tells you the range of f inverse. And if you know the range of f, that tells you the domain of f inverse, right? Because when you swap x and y, the range and domain swap as well. Okay? So that was another sort of property that we had from this setup. Okay, so just giving you a quick reminder here. Now let's jump over to Desmos really quick and just graph these two functions so we can remind ourselves of what it means graphically. So the first function was f of x equals x plus 5 divided by 3. Okay, so it's just this line here in red, and then we had another line, 3x minus 5, and it's this one in blue. And they're both reflections of one another along the line y equals x. And let me just go ahead and change y equals x to a dotted line so you can see what we're reflecting along. So every single point here in blue gets reflected over here to a point in red and vice versa, right? So if we're symmetric around that line y equals x for a reflection around that line, then that's exactly what the inverse means, okay? And again, remember, for example, this point that's here is the point 5, 10, okay? So there's the point 5, 10, and if we swap the role of x and y, it becomes the point 10, 5, and that's right down here. Okay, so the point 10, 5 is then on the red line. And vice versa, if I swap the two, they go back and forth between those two. Every single point on the blue line gets swapped over to something on the red, and vice versa. Okay, so back to our slides. Let's go ahead and practice this method of finding an inverse. And I'm going to let you guys have a few moments to try this one out. And go ahead and let me know with a thumbs up when you're done with finding the inverse. You don't have to type your answer in. I just want to give everybody sort of enough time to try it out on their own. Then we'll sort of do it together, and you can check your work against mine. So as soon as you have gone through the process, give me a thumbs up. Okay, it looks like a couple of people have gone through it. Let me just point out one thing that you should think about before you work on a question like this. You should always be asking yourself, does it pass the horizontal line test? Because if it doesn't pass the horizontal line test, there's not going to be an inverse at all. And that's because if you swap the role of x and y, then you won't pass the vertical line test when you do this sort of switching. And here, if you look at a horizontal line, which we now should know is like of the form y equals a constant c. So let's see, like y equals, Okay. Anyway, I'm not sure why that wasn't graphing as a horizontal line there. But anyway, so if we look at horizontal lines here, we should be intersecting the graph in exactly one spot, okay? And you can see that everywhere on this graph, even if we zoom in on this sort of flat part here, we will intersect the graph in at most one spot, okay? So this indeed does pass the horizontal line test, and it is a one-to-one function. And pretty much any time that we ask you to find the inverse, we're sort of implying that it is one-to-one, but here in this section, we should be really careful, right? Because they're making sort of a bigger deal about it. If this would have been an even-powered polynomial, then we wouldn't be one-to-one, right? None of the even-powered polynomials are one-to-one, and some of the odd-powered ones are also not one-to-one, right? So be careful about this process. But anyway, what you do is you start by replacing f of x with y, and so here we would get y equals 5x cubed plus 1. So this would be the equation of the line in question. I'm sorry, of the function in question. And then what we do is we reflect it along that line y equals x. And again, the reflection process here, the going to the inverse, is just the same thing as swapping the role of x and y. Okay. So here we'll swap y with x, and we get this equation. And this is now the new equation of the inverse. But we want to write it as a function, right? And functions are of the form y is equal to some, expression of x. So we have to go through and then solve this expression for x. I'm sorry, for y. So let's subtract 1 from both sides. We get x minus 1 is equal to 5 times y cubed. Then we can divide by 5 on both sides of this expression. We get x minus 1 divided by 5 is equal to y cubed. Okay, and the last step in this problem is to take the third root of both sides, okay, because we want to undo this 3. So here we'll take the third root here, and we'll take the third root here. And the purpose of taking the third root of both sides is that when you do that, you get back y on this side, and over here you're going to get the third root of x minus 1 over 5. Okay, and once you've successfully solved for y, you can write that as your inverse. So here the inverse of our function f of x is equal to the cube root of x minus 1 over 5. Okay, and that's our answer here, right? So again, the algebra is getting a little more difficult, and the point of this exercise is to show you that the inverse of a polynomial doesn't necessarily have to be a polynomial anymore. It can be a radical function, and that's why we're also talking about radical functions in this one. You should be a bit careful if you were trying to solve this problem and there was an even exponent up here. When you take the root at this point, because it was even, you would have got a plus or minus, and you wouldn't be able to uniquely solve for y, and therefore it wouldn't be a function at all. And we're going to talk about what to do in those types of situations here in a moment. Okay, but again, you just write down f of x is equal to y, you swap the two of them, you then solve for your y. Right? And if the function is 1-to-1, if it passes the horizontal line test, you should be able to do this. The algebra may get a little bit difficult, but you should always be able to do this. And then again, you can always go through and graph this guy so that you can look at whether or not the inverse is what you expected. So here, let's look at the cube root of this expression. So that's going to be x minus 1 divided by 5. And then just remember, the cube root is the same thing as the power of 1/3, right? And here you can see that function there in black. And again, I'll put in that line y equals x and draw it as a dotted line for you. And again, we're just reflecting this curve in red here around this green line to get this one in black. And so we've successfully written down the right equation, right? Because it has that nice symmetry property across that line y equals x. Okay, so that was just a quick reminder of this process. Okay, so let's keep going and talk a bit more about domain and range, okay? Now, one thing that you should have noticed about this graph is that this function here, just looking at the graph, the domain was negative infinity to infinity, and the range was negative infinity to infinity. So for the inverse, the function that we just found, the domain and range are exactly the same as well, all real numbers. But remember, when you find the inverse, the domain and the range swap out with one another. Okay, so here's a question sort of going in the reverse. And this time around, because the answer won't have any sort of radicals in it or roots, I'll ask you to sort of write out your answer in the chat once you're done. So go ahead and go through this one and write out your answer in the chat when you're all done. Okay, so it looks like most of you guys are getting x cubed minus 4, and that's right. So again, the first thing that you should do is just at least verify that your function is indeed 1-to-1. So that's x plus 4th to the power of 1/3. Again, here in Desmos, I'm just writing 1/3 instead of the root. But you can see here in red is the function that we're interested in. And if you look at horizontal lines here, you get horizontal lines that hit this graph in at most one spot, right? So there's no place where it'll hit in two spots, and therefore there will be an inverse. And just as everybody said, the inverse should be y equals x cubed, and then minus 4. And so you can see just like on the graph here that these points, for example, here at 0, -4 gets mapped over here to -4, 0, and vice versa. So indeed, you know, just looking at the symmetry here, we've got the correct answer. So that's another good way to check your work. But let me go ahead and do it on the board just in case somebody didn't get that same answer and might be struggling with the problem. So here, we'll start off by replacing f of x with y. And then you swap the role of x and y. That has the effect of basically flipping us across that dotted green line that we had before. And then we solve for y because we want the formula for the function. And because we passed the horizontal line test, we will be able to do this next step, right? So to undo this third root, you raise both sides to the power of 3. So you get x cubed is equal to y plus 4. And then you subtract 4 from both sides. And so you get x cubed minus 4 is equal to y, and that tells you that f inverse of x is equal to x cubed minus 4. Now, anytime that you're dealing with radicals, you need to be really careful about the domains and the range. But here, because the radical has an index of 3, right? So it has this index of 3, you could plug in anything for x, right? So you can take the third root of a negative number, you can take the third root of 0, you can take the third root of a positive number. However, if this had an even root, then the domain would actually change in that setup. And so here, you should be able to see, hopefully, that the domain is all real numbers, the range is all real numbers, and therefore, for the inverse, the domain and range are all real numbers as well. So indeed, this is that polynomial x cubed minus 4. But there are instances when we won't have functions that are 1-to-1. Okay, so let me go ahead and talk about the process for how to deal with that, and then we'll go through an example, okay? So let's say you have a polynomial, and the polynomial you're looking at is something that does not pass the horizontal line test. In other words, it doesn't actually have an inverse. An example of something like that would be x squared or x to the 4th or x to the 6th. Anything with an even power, right, will not have the property of being 1-to-1. So again, we want to restrict the domain in such a way that the function becomes 1-to-1, right? So the first step that you'll do when trying to find the inverse of a function that is not 1-to-1 is to cut back to the domain. Okay, and sometimes that'll be given to you in the problem, and other times you'll have to just sort of determine what the appropriate region is for the restriction. But your first step will be to restrict the domain, so exclude some inputs in order to guarantee that the function becomes 1-to-1, passes the horizontal line test. And then basically the remaining steps are the same. So you replace f of x with y, you interchange x and y, and then you solve for y. And you rename the function f inverse, right? And you have to be careful. As you're solving for y, your domain restriction will be important because your original function didn't satisfy the horizontal line test and is not 1-to-1. You won't be able to do step 4 uniquely, right? There's going to be a plus or a minus, or there's going to be some issue about a choice that you're going to have to make. And so based on what you made for the restriction, that will inform what you choose for your y. Okay, and then it says revise the formula for f inverse by ensuring that the outputs of the inverse function correspond to the restricted domain. So then they're just saying make sure that you didn't make the wrong choice, right? Because often it'll be a plus or a minus, and you have to determine Is it the plus that you need to keep or the minus that you need to keep? And if it's going to be a function, there can't be any plus or minus, right? Every input has to lead to exactly one output. Okay, so that's the process. And it's essentially the same with the exception that you have to sort of figure out where your domain is, okay? So here's an example, okay? Same formula, x minus 4 squared, however, different domains, right? So the comma here with the extra piece of the domain means that you're going to be looking at a different region. So let's just go ahead and graph this one really quickly in Desmos so we can all see it. X minus 4 squared. And we switch over. Okay, so here is our graph of x minus 4 squared. And you'll notice that certainly if I look at the horizontal line here at y equals 4, it hits the graph in 2 spots. So this particular function is certainly not one-to-one. And therefore, if we just tried to write down the inverse for it, the inverse would not be a function at all, right? So for example, you would first replace the f of x with y, and you would get the same function, sort of following the steps that we've been talking about. But then, like I said, your next step is to replace x with y. So here I would replace that y with x, and this x with y. And we get a function that does reflect across this line, right, or a relation here that does reflect across this line, but you'll notice it doesn't pass the vertical line test. So we can't just go through and simply do this, right? We have to think about a restriction to our domain. And here in infinity, you can add a restriction to your domain by adding sort of curly brackets and writing down the restriction. So here, this is going to be x is greater than or equal to 4. And so now you'll see that it only graphs the region where x has a value greater than 4. And if you now look at this function over here, indeed it is one-to-one. Okay, so this is one potential restriction of our function that then gives us a one-to-one function. Again, we have to restrict that domain. Another possible restriction is given in part B of this problem, and that's basically to the left of 4. In other words, x is less than or equal to 4, and that's this side of the graph, okay, the left side of the parabola. And you can see again that if we just keep that part of the domain restricted to those numbers that are less than 4, then again, we're one-to-one. And when we're trying to find the inverse in these cases, we have to take both of those into account. So let's go through and figure out what the inverses are for each of these. So again, that comma with the x is greater than or equal to 4 or less than or equal to 4 is just indicating to you that the domain has been restricted. Okay. So here we're going to look at f of x is equal to x minus 4 squared. Our first step is to look at y is equal to x minus 4 squared. Again, just replacing f of x with y. Then we swap the role of x and y. And like I said before, this is no longer a function, right? So when we do this step here, we're now at something that's no longer a function. And so we won't be able to actually solve for y uniquely. And we can see why. If we tried to take the square root of both sides at this point, we get plus or minus the square root of x is equal to y minus 4. So here, because this is an even power, when we take the square root, we get two possibilities, either the positive or the negative. And then the final step here would be to add 4 to both sides. And if I add 4 to both sides, I get y is equal to 4 plus or minus the square root of x. And this is not a function, right? Because if I plug in a value of x, I don't know if I should keep the positive or the negative. Okay, and this is where, in part A, the fact that x is bigger than or equal to 4 is going to play a role. Okay, so which of these should I keep if I want to control this, right? Well, let me remind you that at this stage right here, so these two are sort of linked together, at this stage right here, we should have also flipped this as well, right? So at this point, this should be basically telling us that y is greater than or equal to 4. Okay, so if y has to be bigger than or equal to 4, do we keep the positive or do we keep the negative? Yeah, we need to keep the positive because the square root is positive, and if I add something to this, it's going to make it bigger, right? And so this fact right here that we were dealing with y is greater than or equal to 4 tells us in this case that we're going to get y is equal to 4 plus the square root of x. And for part A, we've got f inverse is equal to 4 plus the square root of x. So when we're dealing with this domain restriction for this function, we do have an inverse, and this is it, okay? But you'll notice that the domain of this function is not all real numbers, right? The domain of this function here is all numbers greater than or equal to 4. So from 4 out to infinity. And that's because the domain of, the range of this function had that property. So let's go ahead and graph those in Desmos just so we can see what I'm sort of talking about here. Here, we're going to be interested in, again, the case when x is greater than or equal to 4. So that was part A. And so that's that red graph that you're seeing there, the right half of that parabola. And we went through and we saw that we should do 4 plus the square root of x, right? So here, let's write down the function 4 plus the square root of x. And you can see that in that case, it is indeed reflected along that line, y equals x, okay? So we've reflected the red parabola to that green dotted line there, and that's the correct domain restriction. However, if we had a domain restriction that was as follows, less than or equal to 4, then the graph wouldn't match up. And you can see that that line in green there is not the correct inverse. Now, the way that we change things in order to get sort of the correct answer here for that step, for B, like let's say we were doing B instead now, that means that x is not greater than or equal to 4, but less than or equal to 4. Well, that means that when we do this swap over here, we wouldn't get y is bigger than or equal to 4, we'd get y is less than or equal to 4. And so here, instead of kicking the plus, we would have to be smaller than 4, so we'd have to subtract. And over here, we would subtract as well, okay? So for part B, it's just 4 minus the square root of x. It's the other choice, right? And the domain restriction told us which of the two choices that we should be going with. So let me go ahead and just show you that here. If I were now to put 4 minus the square root of x, you can see that indeed now this green line is the reflection of the left half of that red parabola. Okay, so the domain restriction that you're given informs the formula for the inverse, right? And the restriction that you take is making sure that whatever the function you're given is 1-to-1. Now, this isn't the only restriction we could have done. There are other restrictions as well. We could have looked at something like x is bigger than 5 or x is bigger than 100. But it's the one that was given to us in this particular one. Now, there isn't a unique choice for the domain restriction, but it really just depends on the problem that you're working on. So here it was just sort of given to us. Okay, so that's this business about domain and range. And again, it's really an issue when the polynomial has an even degree, right? So if I were to multiply that whole thing out, the leading coefficient would be an x squared, and that would mean that we'd have a polynomial of even degree. So we're going to run into these domain issues anytime we have an even degree one. Also for odd degree ones too, right? There can be some odd functions where we might have multiple turning points. And anytime you have those turning points showing up, you're going to be not 1-to-1. Okay. So let's keep going with a few more examples. Here, this one's telling us that we need to restrict the domain and then find the inverse. And here, this is a bit of a misnomer. There's no domain that we're going to have to restrict. This one is actually from infinity. And what they just mean here is that the domain is not all real numbers. So let me give you guys a moment to identify what the domain of this function is. So this is another good example from a sort of a question from the midterm exam. What is the domain of this radical function? So go ahead and just post that into the chat as soon as you figure out what the domain is. Okay, yes, so, and here we should be really careful about if we mean the domain of f or f inverse, right? So the domain of f of x, the function that we're given here, is 4 out to infinity, okay? And the way that you get that is you just say, okay, well, the stuff underneath that radical has to be greater than or equal to 0. So then you just say x is greater than or equal to 4. Okay, moving that 4 over to the other side. And then in interval notation, it looks like this. So for example, we couldn't plug in 0. If we tried to plug in 0 into this function, we get the square root of negative 4, and we wouldn't get a real number, so we couldn't put it on our graph. Okay, so that's the domain of f of x, and that means that the range of this function, right, the range of the inverse function is going to be something like 4 to infinity. And so let's go through and try to write out the equation, and we'll see what they mean by restricting the domain. They're actually not talking about the restricting the domain of the function f, which is what it sounds like here. They're talking about restricting the domain of the inverse. So let's go ahead and solve for the inverse here, right? So go through, and remember, this is a little bit different than the last time, because last time we were looking at a cubic root. This is a square root. So this is an even power. So go ahead and find the inverse function. It should be a polynomial, and then we'll talk about how to restrict its domain to get the right answer. Okay, cool. So pretty much everybody's writing out the right answer here. So again, I'll just go through it really quickly. Y is equal to the square root of x minus 4. You square both sides. Y squared is equal to x minus 4. Well, I'm sorry. Let's follow my steps. We'll swap the x and y first. It doesn't matter when you swap the x and the y, but I typically will swap it at first. So let's just stick with that. Now we'll square both sides, and we get x squared is equal to y minus 4. And then we add 4 to both sides. So we get x squared plus 4 is equal to y. And it's almost enough to write out f inverse of x is equal to x squared plus 4, but this is not quite correct. Okay? And the reason this isn't correct is that this has too big of a domain. Okay? This thing has too big of a domain. And maybe it'll be a little more apparent if I graph these two functions in infinity, and we see what happened here. Okay? So if I look at this function in infinity, I'm sorry, in Desmos, it is the square root of x minus 4. Okay, so there we are with this function in red, and we would like to reflect it across this line in purple. And we just went through the process of like sort of going through that, and we got y was equal to x squared plus 4. And you can see the problem is the fact that we've included these values over here, right? Because there was nothing below the x-axis on this red graph, and so nothing is going to get reflected to these values over here. One way to think about it is that over here, if we focus on this function f of x, we can talk about its range of f of x, okay? And the range of f of x, let's think about it, it's this square root function. The square root is always positive, right? And the smallest it could ever be was 0. I mean, we could just look at the graph like we saw, that red function. It starts off at 0 and goes all the way up to infinity. So the range here is going to be from 0 to infinity. And so what that means is that the domain of f inverse is 0 to infinity. So it's not quite this parabola x squared plus 4. It's the parabola x squared plus 4, but we have to also guarantee that x is bigger than or equal to 0. Okay? And let me go ahead and graph that over here in Desmos for you. You can see now that if I add this condition that x is bigger than or equal to 0, I indeed get this right half side, which is the reflection of this graph in red. Okay, so just coming back here to the statement of the problem, it says restrict the domain of the function. They don't really mean the domain of the function, they mean the domain of the inverse, right? So here, even though you can find a formula for the inverse, you have to be careful about whether or not this thing is one-to-one, okay? So we're getting a little more nuanced with our understanding of one-to-one and inverse functions. Let's hit one more here that's a little tough on the algebra. And I'm actually was pretty impressed with the midterm exam. A lot of students really nailed, there was a question, I think, on some versions of the midterm that looked almost identical to this sort of thing, and a good chunk of students got through the algebra. So let's just go through this one. And here, I'm not going to focus so much on the domains and ranges. I'm going to focus more just on finding the inverse, because it's the algebra that I think is a little more interesting here. So again, we've got y is equal to x plus 3 over x minus 2. And we can say a few things about this function, right? We can say, for example, that it's got a horizontal asymptote at y equals 1 because the degrees are the same on the top and bottom. We can see that it indeed has a vertical asymptote at 2 because the denominator would be 0 there. It's got a root, an x-intercept at -3, right, a 0. So we already know quite a bit about this function. And what we would like to do now is try to compute its inverse, okay? So here, your first step is to replace x with y. And then go through and try and solve for y, okay? And this is one that students sort of, if they did mess up, they messed up. Not this step. Most students really multiply by the y minus 2, so they realize you had to clear out the fraction. So you multiply both sides by y minus 2. But the part that really sort of got people on the midterm was this step over here. You have to distribute your x, right? This isn't just x times y and then minus 2. This is x times the whole thing, y minus 2. So this is xy minus 2x is equal to y plus 3. And once you clear out all of the fractions, you could just move everything with a y to one side and everything without a y back to the other. So here I'll have to move this y to this side and the 2x to the other side. So this is xy minus y is equal to 3 plus 2x. So I just added 2x to both sides here and subtracted y from both sides. And that had the net effect of making sure that all of the y's were on this side. And the reason why I want to put all the y's on this side is now I can factor it out, right? I can do this step in reverse. So I factor out that y, and I get x minus 1 is equal to 3 plus 2x. And then my final step here is to solve for y, and I get y is equal to 3 plus 2x over x minus 1. And so the inverse of this rational function here is now 3 plus 2x over x minus 1. And notice some cool things are happening here, right? So remember, we said that this had a vertical asymptote at 2. So that vertical asymptote, when I reflect along that line y equals x, becomes a horizontal line, right? And it's going to become a horizontal line at a y value of 2. And you can see that here the leading coefficient is 2, and this one's 1. So this has a horizontal asymptote at y is equal to 2. So we're seeing that. And then also, this one had a horizontal asymptote at y equals 1, and when we reflect that, we get a vertical line at x is equal to 1. And so you can see here that this also has a vertical asymptote at x equals 1. So we're sort of seeing some of the pieces of what we would imagine to happen in the graph, just sort of in the statement of these two rational functions. Okay, and again, the thing that you should be focused on here with this example is this step, right? This is the step that a lot of students really messed up. And the goal of this step is really to get all the y's on one side. Okay, so that was that guy. And then I guess we have one more. And again, this one's from Edfinity. And you'll notice that it has a domain restriction. This one's a little bit different than the others because we've got these extra pieces here where it's a radical and a polynomial, right? So a little more complicated than the other example, but you'll go through it in exactly the same way, okay? So here we'll have to take into account the fact that x is greater than 0, right? And again, the reason why we're making this domain restriction is that if we were to actually just graph this function, it wouldn't pass the horizontal line test. We need to restrict our attention to the values of x that are greater than 0 in order for this thing to actually pass that horizontal line test. Okay, and we'll see that showing up when we're solving, right? This x is greater than 0 is going to help us make a choice about some plus or minus that's going to show up in the formula. Okay, so here I'll just write it out as y equals, again, the square root of x squared plus 5x. And again, we're making the domain restriction that x is greater than 0. And the purpose of that domain restriction is to guarantee that we are indeed one-to-one, so we do have a unique function for the inverse. Okay, so your first step again is replace the x's with the y's, right? So this becomes x is equal to the square root of y squared plus 5y, and then this one becomes now y is greater than 0. And we're going to use this fact that y is greater than 0 to tell us which of the plus or minus to choose, okay? So here we've got to go through and solve this thing for y. So let's try it. We'll square both sides first. And we get this expression. And there are a few ways to approach this problem. One is to move the x squared to the other side and then use the quadratic formula, which I think is probably a little more difficult and time-consuming because you'll have to simplify everything. But the better way is just to complete the square on the right-hand side, okay? So let's think about completing the square. What do I need to add to both sides of this equation in order to complete the square on the right-hand side? Now remember, it's this b over 2 squared business. So what should we be adding to both sides of this this polynomial? So again, we're focused on this side here. We're looking for the term that is next to the variable with degree 1. That's this. That's your b. And then we want to do b over 2 squared. That's what we add to both sides of the equation in order to complete the square. Well, we don't want to include the y, right? Remember, the b is just the coefficient of that term. So think about this as being sort of a parabola in y as opposed to a parabola in x. Okay, that's right. So Blake has the right idea here. The b is 5. We divide by 2 and square it. In other words, this is 25 over 4. Okay? So the term that needs to complete this square is 25 over 4. So how does that help? Well, over here, we're going to get x squared plus 25 over 4. And we'll get y squared plus 5y plus 25 over 4. And now that we've done that, this is a perfect square. So this factors, and it factors into y plus b over 2. In this case, the b is 5. So this is 5 over 2 squared. And on this side, we get x squared plus 25 over 4. Okay, so now what we can do is try to solve for y. So we'll take the square root of both sides, and this is now where we get a plus or minus. So here we'll get plus or minus the square root of x squared plus 25 over 4 is equal to y plus 5 over 2. And then your second to last step here is to subtract this 5 over 2 to the other side. And when you do that, you get y is equal to negative 5 over 2 plus or minus the square root of x squared plus 25 over 4. And now this is where we're going to have to come back and think carefully about our domain restriction, because now we have this thought that y had to be greater than 0. If y has to be greater than 0, should we pick the positive or the negative here? Yeah, it should be positive, right? Because if we were to pick the negative, then it would just be a negative minus a negative. The whole thing would be smaller than 0. So here we need to keep the positive term, and so we get f inverse of x is equal to negative 5 over 2 plus the square root of x squared plus 25 over 4. Okay? And this is the formula for the inverse in this case. And again, it depends on what our domain restriction was back up here. Okay? So you'll notice that because this thing without the domain restriction is not one-to-one, we couldn't solve for y uniquely. But once we made the domain restriction, we could then say, okay, there is a unique formula for the inverse. And that's the purpose of that nice sort of domain restriction that we have there. Okay, and that's it for this assignment. I think a lot of the homework questions are pretty straightforward here, so you know, this is mainly just a reminder of like review stuff, right? And the new thing here is the sort of domain restrictions and the connections back to polynomials. Well, have a nice day, guys.